We're finally ready to define this formal system of deductions that I'm calling Z infinity. A deduction in Z infinity always has a conclusion. A deduction is supposed to be a formal argument that shows that something, the conclusion, is true. In Z infinity, these conclusions are finite multisets of sentences in negation normal form. We know what it means when the conclusion is a single sentence. It means we've demonstrated that the sentence is true. What is it going to mean to conclude that a set of sentences is true? It means that one of those sentences is true, but we don't necessarily know which one. For example, we will later show that for any sentence phi in negation normal form, we'll be able to deduce the multiset phi with the negation of phi. Notice a little bit of notation. This symbol is called the turnstile. So this means there is a deduction in Z infinity whose conclusion is the multiset phi comma negation of phi. Notice that we're using the squiggly negation because all our sentences should be in negation normal form. So after we've defined our system of deductions, we'll prove that we can always deduce the multiset with phi and the negation of phi in it. And that just means we always know either phi is true or phi is false, and then the negation of phi is true, but we don't necessarily know which one. So a multiset gives a bunch of possibilities, and we're committing to at least one of them being a true thing. It's hard to see at first why we define our system this way. The best thing to do is to dive in, see the formal system, and then once we start seeing it in action, we'll start to see how it works. The most basic deduction rule we could have is that if something is obviously true, we should be able to observe that it's true. We should be able to deduce it. For us, the formulas whose truth is obvious are the atomic sentences. The atomic sentences are all pretty simple. There are qualities or inequalities between two terms whose values we can calculate. So if an atomic sentence is true, we can just calculate the two sides and observe that it's true. So there will be a rule that says whenever phi is a true atomic sentence, Z infinity deduces phi. In keeping with the idea that we only need one thing in a multiset to be true, the rule will actually be a little more general. If gamma is a multiset which contains a true atomic formula, then Z infinity can deduce gamma, the whole multiset, because gamma is justified by the true atomic sentence that it contains. Dually, if phi is a false atomic sentence, then the negation of phi is a true sentence, and we also consider it simple enough to just notice that it's true. So if gamma is a multiset which contains the negation of a false atomic sentence, Z infinity can deduce gamma. This is regular negation, because we're allowed to negate atomic sentences in negation, not normal form. All our rules will have names. We want to be able to talk about what the justification for a conclusion is. We think of both these cases as a single rule, which we call the true rule. This is our axiom. It's a rule that stands by itself. We don't have to have already justified something else to use this rule. Atomic sentences are the only ones we consider obvious enough to just observe their truth. Everything else has to be justified using multisets we've already justified. Most of our rules are tied to the syntactic form of a sentence. For instance, we have a rule which lets us deduce phi and psi. How would we justify that phi and psi is true? We would justify phi and also justify psi, and say that since we've justified both of them, we've justified phi and psi. Again, we have to take into account multisets. So the actual rule says, if we deduce a multiset gamma together with phi, and also the same multiset gamma together with psi, then we can conclude gamma together with phi and psi. We use this notation, which is very common in proof theory, where instead of writing a union of sets, we just write a comma to mean adding an extra formula. We write I wedge for the name of this rule. That stands for and introduction. The rule introduces the formula phi and psi. Notice, and this is typical of our rules, we have this whole multiset, but the rule only touches one formula in the multiset, and gamma, the rest of it, is left alone. That formula that we manipulate, phi and psi, is called the main formula. of the rule. Once you've seen the pattern, the other rules aren't too different. There should be an IV rule, an OR introduction rule, which introduces phi or psi, and it has two forms. If we've already justified phi, we can justify phi or psi. Alternatively, if we've already justified psi, we can justify phi or psi. Again, there's a multiset gamma floating around in the background, and phi or psi is the main formula. We need an I for all rule, a for all introduction rule. This is the infinitary rule in our system. What we say is, suppose that for every n, we have a deduction of gamma together with phi of x maps to n. So for every, all infinitely many natural numbers n, we've concluded that either something in gamma is true, or phi is true of n. Then we can conclude gamma together with for all x phi. The exists introduction rule is simpler. If we know that for a single term t, we've justified gamma together with phi of t, then we can justify gamma with exists an x phi. And of course, phi with x replaced by t should be a sentence, so t should be a closed term, a term with no variables itself. These four rules, collectively, are called the logical rules, because they're fundamentally about how the logical connectives and quantifiers behave. The next rule is called the weakening rule. It says that if we've deduced a multiset delta, and gamma is a bigger multiset, so delta is a subset of gamma, then we can also deduce gamma. This makes sense because if delta is justified, then at least one of the things in delta is true, and gamma just has more options. It's easier for gamma to be justified, so we can deduce gamma as well. We call it weakening because we're weakening our conclusion. The weakening rule is what's called a structural rule. It doesn't really contain interesting logical content. You might wonder, why would we ever want to weaken our conclusion? And the answer is, for technical reasons, to make the real rules, the logical rules, fit together the way they're supposed to. There's a second structural rule, the contraction rule. If we deduce gamma with two copies of phi, then we can combine them into a single copy of phi. If either phi is true or phi is true, then phi is just true. We find it convenient to work with multisets rather than sets for technical reasons that involve bookkeeping how sentences were justified, but the contraction rule says whenever we have multiple copies, we can always combine them. There's one final rule, which we'll spend a lot of time thinking about. Suppose we've justified gamma together with phi, so either something in gamma is true or phi is true, and suppose we've also justified gamma and the negation of phi. Again, we want to stay in negation normal form, so we're using squiggly negation here. So either something in gamma is true or phi is false. Well, we can't have phi be true in the first part and the negation of phi be true in the second part, so something in gamma must be true either way. So if we've deduced both gamma with phi and gamma with not phi, we can deduce just gamma. We call this the cut rule. You can think of this as corresponding to a proof by cases. What we want to prove is gamma, so we first consider the case where phi is false, and then we consider the case where phi is true, and if we can prove both of them, then we've proven gamma. That's our final rule. The proof system Z infinity consists of the axiom true, the four logical rules, the two structural rules, and the cut rule. And that's a complete description of what is justified. It's an inductive definition. The things justified by the true rule are justified, and the other rules tell us if certain things have been justified, then additional things are justified. These may seem sort of opaque, but they'll be at least a little clearer once we see some examples. One quick point. We really do intend Z infinity to be a formal, technical definition. When I imply that it's a proof system, I'm not making any kind of philosophical claim about these rules. I'm not claiming that they're a good representation of logical reasoning, or that we should use them for any purpose other than the technical proof for which we're going to use them. It's helpful to get used to working with the system if you see how it was inspired by ordinary mathematical reasoning. For example, how the and introduction rule is motivated by the way working with phi and psi is done in ordinary mathematical reasoning. But when it comes to justifying these rules, when it comes to asking why did we pick these rules and not some other rules, the justification is that we will be able to deduce exactly the things where we want to be able to deduce and will not be able to deduce things we don't want to be able to deduce.